Okay, good morning. Today's lesson is supposed to be this topic, the greatest common divisor and the least common multiple, but I realized that I haven't completed what we started before, so let us start to complete the topic of prime numbers, which is of course related to this as well. So we discussed about the prime numbers. We defined a prime number. We also defined a composite number. And then I told you that we exclude 1 from being a prime number, because if we insist to keep 1 as a prime number, you remember what will happen then? Yes?
All non-prime numbers will have an infinite amount of ways to describe them
As a product, yes. So if we exclude 1 from being a prime number. So let me write something. So here we have two theorems. In the book, they are expressed but without proofs. Okay, so theorem. Theorem, you know that it means that a statement that is true. What is the difference between a theorem and axiom? Axiom is also a statement to be is true, but a statement is accepted to be true. But a theorem we have to show, we have to bring an argument why this is true. Okay, so it means that whenever I talk about the theorem, there should be a proof for it, but sometimes the proof is beyond the scope of the lesson, so this is why we eliminate the proof. Okay, so theorem 1. So let me just write a theorem here. Every natural number greater than 1 has a prime factor. Okay, so we don't want to prove it, but this is very easy to understand. So if you choose any natural number which is greater than 1, then definitely that number has a prime factor. For example, if you choose 7, what is the prime factor of 7? Do you know what a factor is? Factor or divisor? Yes, factor means something that this number is divisible by that one. Yes, so when you say, do you remember this symbol when I write A, this symbol B, this means B is divisible by A, so I'm just reviewing this, okay? Or you can say that B is a multiple of A. This is the way that you read it from right to left, two methods, and then two other ways that you read it from left to right. So the common one is A divides B, or you say A is a divisor or factor. They mean the same thing. So let me underline these. These are this one of A is a divisor of B. Okay. So these are the ways that they are equivalent. When I say B is divisible by A, I mean A is a divisor or a factor of B or something like that. So this is the way that we read it. So when I ask you, can you give me a factor of 7? Or a divisor of 7? I mean, can you give me a number so that 7 is divisible by that number? Okay? So 7 is divisible only by 1 and 7 itself. And this theorem claims that every natural number greater than 1, for example 7, has a prime factor. So if I ask you, is it correct for this number at least that there is a prime factor for 7? Yes, 7 itself. Yes? Is there any, so for example, this claims that 6 is a so 6 is a number greater than 1. So this claims that there is a prime factor for this one. So at least in this case there are 2 prime factors, but at least one of them is guaranteed. One of them is what? 3, and the other one is 2. So okay, so let me clean this up because we don't need it anymore. So this is a theorem, but the main theorem is called the fundamental theorem of arithmetic. And what is that? So the content is that every composite number, you remember what's a composite number? A composite number is a number that is greater than 1, which is not a prime number. So every composite number can be written as a product of prime numbers. Can uniquely be written. Let me write like that. Can okay, but when I say uniquely, I mean up to the order of the factors. Yes. For example, if I give you 24, you can write it as 2 times 2 times 2 times 3. So 24 is a composite number. You can write it as the product of only prime numbers. And this is unique. Of course, if you consider the order matters for you, you lose the uniqueness. But if you don't care about the order in which these numbers appear in this product, then it is unique. Okay? And that is the reason that we chose to exclude 1 from being a prime number, because if you insist to keep 1 to be a prime number, then you lose this uniqueness, because someone might write this, someone might write the same thing with an extra 1 at the end. Someone might write the same thing with 2 extra 1s at the end. Yes, all of them will be the product of prime numbers. So this is why it's a matter of taste or convention. So we exclude 1 to be from being a prime, then I can ask you about the factorization. So I can ask you 24, factorize it to a prime number, the product of prime numbers. So this is also a theorem. It's a very fundamental theorem. This is why probably the prime numbers are so important, because even if you have a composite number, this is guaranteed by this statement that you can always write it as a product of only prime numbers. So somehow, if you have a good understanding of prime numbers, you can have a better understanding of whole numbers, yes? Because every number can be written as a product of prime numbers. Okay, and then what we told last time is the number of prime numbers is infinite. We will be able to prove it later, but not now. So the list of prime numbers, the smaller one is 2, and then 3, and then 5, 7, 11, 13, and etc. Might be intuitively this is not that clear, because intuitively I was feeling, when I was at your age, I was feeling that, okay, if I have a very big number, the chance of that number being divisible by at least one of the numbers before that is quite high. But of course it might be quite high, but still Euclid was able to show with a very simple argument that we will study later, that the number of prime numbers is not finite. It's infinite. Okay, so that is important. That's also a theorem. We will study that later. So Euclid actually was able to prove it. So there are infinitely many prime numbers. And if you remember, I talked about this. This is always, it's not that easy to find if a number is a prime number or not, if the number is very big. And if you remember, I showed you the largest prime number discovered was 2 to the some power of 82 millions or something, s minus 1. Yeah. So, so it is not that easy to realize if a number is prime or not, but of course, there was an algorithm that we could, for example, let me give an example. If I want to see if 251 is a prime number or not, it is not a hard problem. If you have a calculator, you can start dividing this number by all the previous numbers to see if it is divisible by any one of the previous numbers or not. If you tested all of the previous numbers and it is not divisible by any one of them, so this means that this is a prime number. If during the process you found a number for which this is divisible by, you end up the process and say that this is not a prime number. Okay? But of course, checking all 250 numbers before that is not needed really. So you don't need to go beyond 126. Do you agree? Because 126 is more than half of this number. So there is no point for dividing this number by numbers above 126 because there is no chance that this division becomes an integer. Yes? So, okay. So instead of checking 250 numbers, you can limit yourself and check only 126 cases. It is better than the previous one, but it's not that good enough. So another mathematician, he's not a modern mathematician, old age mathematician for the ancient time, I think. I don't remember exactly the date, we can check it out. He was able to do it even better. He realized that instead of to understand that if this is a prime number or not, what we need to do is just take the square root of that number. Let us see. So 15 to power 2 is 225. 16 to power 2 is 256. So this number, whatever it is 15 comma something, yes? So approximately 15. Okay, he said that, okay, if you list all the prime numbers smaller than or equal to this number and check the divisibility of this only by that list, it is enough. For example, here, what are the prime numbers smaller than or equal to 15? It is 2, 3, 5, 7, and 11, and finally 13. Okay, so how many numbers I have in my list? 1, 2, 3, 4, 5, 6. So he was able to show that if you divide this number by this list and none of them, this is not divisible by none of them, then it means that this is prime. And if it is divisible by one of them, then it is not a prime number. So it is much faster way. But of course, I told you that this method, even though is much faster than the previous methods, it still is not good from that very big number. Because say that the number that we had is 82 million something. If you take a square root of that, it becomes 2 to the power of 41 million something. Yes? So even 2 to the power of 41 million is extremely big number. It's much better than 2 to the power 82 millions, but still there is a lot number in my list. Okay? So, but that is better than nothing. So here, finally, do you think that 251 is a prime number? Let us check. We take the square root. Whatever I get, I list the prime numbers smaller than or equal to this number, and I start dividing. Is 251 divisible by 2? No, it is not even. So this, I can check it out immediately. And 251 is divisible by 3. Do you remember the rule for divisibility by 3? 2 plus 5 plus 1 is 8. 8 is not divisible by 3, so it's not divisible by 3. Is it divisible by 5? No. So then 7, 11, and 13. So you check only divisibility of 251 by these numbers, okay? So then probably it is not divisible by any of them. So this means that you don't need to look more. It is guaranteed that 251 is a prime number. Yes? And then I told you that in GeoGebra, how do you ask? Do you remember? Capital S, capital prime is prime. And then you put this number inside. If you get true, it means that this is prime. If you get false, it means that this is not a prime. Yes? Is that clear? But why this is correct? So we want to understand, this is also given in the book. We want to understand why this method that I described is correct. So theorem. So let me write like this. Every composite number n has a prime factor p such that p is less than or equal to square root of n. So what I'm claiming that if you give me a composite number n, I can always find a prime factor of n, which is less than or equal to the square root of the number itself. Yes, this is the claim that we want to show. This is true or false. Okay. So this I will write proof because I told you that theorems always have a proof. So we say that let me write like this. Since n is a composite number, then n can be written as the product of a and b such that 1 is less than a, less than or equal to b, less than n. Okay, first I want you to understand what I have written is understandable for you or not. I give you a composite number n. When I say a number is composite, it is not a prime number. Okay? I am claiming that whatever composite number I give to you, you can always write it as a product of two numbers so that none of them is equal to 1, none of them is equal to n. They are greater than 1, they are smaller than n, and then of course one of them is at most equal to the other one. I call the smaller one a, the bigger one b. Yes? For example, if I give you 16, you can write 4 times 4. In this problem, a is 4, b is also 4 in this case. If I give you 21, you can write it as 3 times 7. Yes? What is the a here? A is 3, b is 7. So it doesn't matter. Whenever I give you a composite number, you can always write it as a product of at least 2. At least 2 numbers. Of course, here in this case, 4 can be written as 2 times 2. This 4 can also be written as 2 times 2. Okay? So for example, 12. So let me write it as 24. So 24 can be written as 3 times 8. Yes? I'm not saying this is the factorization of 24. What I'm claiming is that when I give you a composite number, that composite number can be written as the product of at least 2 numbers so that none of them is equal to 1. Is that clear? And then one of them is smaller than the other one or at most equal to the other one. In this notation, I chose A to be the smaller one, B to be the bigger. Yes? So is this understandable now? So when I say n is a composite number, it means n can be written as a product of 2 numbers with these conditions. First of all, tell me, do you understand what's going on? Okay. Now, since a is greater than 1, based on this theorem, every natural number greater than 1 has a prime factor. Yes? And now since a is greater than 1, a has a prime factor p. Yes? A is greater than 1. According to this theorem, a has a prime factor greater prime factor, which I call it p. What is the meaning of prime factor? So let me write it with a different color. So it means that p divides a. Yes, when you say p is a factor of a, it means that p divides a, or a is divisible by p. Okay? Okay, now on the other hand, what is a? A is less than or equal to b. Yes? And then I multiply both sides by a. Yes, so this becomes a squared. The right hand side becomes a times b. Yes? But this means that, what is the name of this? A times b is n. So this means that a squared is less than or equal to n. Okay, and then what can I say about a? A is less than or equal to a square root of n. Yes? Is that understandable? So I started from this assumption. I hope that you don't lose the track. So you told me this is obvious for you after I explained it for you. So then, if this is obvious, then I erase it from my memory. I know that this is true, so I use it. How should I use it? In this case, I take this assumption and write it here, and then multiply both sides by a, and I get that one. If I ask you what is a dot b, you say that this is n. So instead of a dot b, I put n, and then I can take the square root, and then I get that. Yes? So I know that a is less than or equal to square root of n. Okay, and then you are telling me that p divides a. Yes? So this means that p also divides n. Do you agree? Because if a itself is divisible by p, the whole combination is also divisible by p. Yes? Is that clear? If only a is divisible by p, then a times b is also divisible by p, because when you say a times b divided by p, if you know that a is divisible by p, they can be simplified and the answer becomes an integer. Okay, so it doesn't matter how much I'm multiplying by. So if p divides a, then p divides n, and then what do I have? I have so this is one thing, I want to keep it. And then you come back here, a is less than or equal to a square root of n. Because p divides a, p is also less than or equal to a. Yes? You see, from p divides a, I can conclude two things. One thing is that p divides n. One thing is that p is smaller than a. Okay, now look, p is less than a is less than a square root of n. What can I conclude? I can conclude that p is less than or equal to square root of n. Yes? So what I did, I was able to show that for n, I was able to guarantee the existence of a prime number, so that that prime number is a factor of n on the one hand. On the other hand, that p is less than or equal to a square root of n. So this is always guaranteed that I can find such a p. Yeah, is that clear? Now, if I want to give it in numbers, if you are not confused, let us try to test it with 21. Yes. So let me write 24. Let me write it as 4 times 6. Okay. So you give me 24. I write it as 4 times 6. Yes. Take the smaller one. Let us say 4. Okay. 4 has a prime factor. Yes or no? What is the prime factor of 4? 2. Yes. So 2 is a prime factor of 4. Is 2 a prime factor of 24 as well? Yes, because 2 divides. So this is clear. When 2 is a factor of 4, it is also a factor of the product. Yes. So 2 is a factor of that product. Okay, and then this is definitely less than or equal to 6 to power 2. Yes. Yes. Sorry. So this is 4 is less than or equal to 6. What I did there, and then I multiplied both sides by 4. So this becomes 4 to power 2 is less than or equal to 4 times 6. Yes? And then it is clear that 4 is less than or equal to the square root of 24. So for numbers, it is very trivial. You don't need even to think. But you want to write it in as a proof, you have to write it in that way. Any questions? Do you understand what's going on? Because I see a lot of these kinds of exercises in the book. So you have to have a good reasoning. So this tells you that if you give me a composite number n, it is guaranteed that I can find a prime factor for that number, which is less than or equal to the square root of that number. Okay, I want to wait for you. Of course, this is a very abstract proof. Okay, so that I want to make sure that you understand what is going on. Yeah, is that clear? Or not? You can say something. Okay. So every composite number n has a prime factor p, which is less than or equal to the square root of n. Okay, now can you understand how can I conclude this algorithm using that theorem? Yes? Do you remember what was this algorithm? This algorithm told you that if you want to see if this is a prime number or not, take the square root of it, okay, and write all the prime numbers before that number. If this number is not divisible by any one of them, it is not a prime number. Why do you think this is a consequence of that theorem? Yes?
Because if it is divisible by any of the numbers, any of the prime numbers smaller than its square root, then it's a composite number. But if it's not a composite number, and it's greater than 1, then it's a prime number.
Yeah, exactly. So what is it telling you? So the consequence of a theorem in mathematics has a name. It is called corollary. Okay. So you don't need to be worried about these names. Corollary means the consequence of that theorem, what we can conclude directly. Okay. So if n does not have a prime factor, so does not have a prime factor that is less than or equal to square root of n, then n is not composite, yes? Do you understand? This is an immediate consequence of what we showed, yes? Because you tell me if n is composite, then there is a prime number which is less than or square, there is a prime factor which is less than or equal to square root of n. It means if n does not have a prime factor which is less than or equal to this, then it is not composite. Because being composite guarantees existence of such a factor. Yes? Okay, but no one writes n is not composite. People write what? N is a prime number. Yes? I just want to understand that that is the theorem. That is the immediate consequence of that theorem. Yes? So the mathematician was, I think, so Eratosthenes, yes. He was actually the one who discovered this rule. Yes? Any questions? Okay, I see question marks on your head. Do you have questions? So which part is it understandable for everyone? Yes or no? Okay, so let me repeat it again, okay, because this is something a little bit abstract. What is my goal? I give you a composite n, a composite number. My goal is to prove for you that there is a prime number so that this is divisible by that. And secondly, this is less than or equal to a square root of n. At least you understand the statement. Yes, the statement is that if you give me a composite number, it is always possible to find a prime number p such that n is divisible by p and p is less than or equal to the square root of the number I gave you. At least you understand this content. Yes, this is what we want to show. Yes. I will come to it again. So I will repeat the process. But at least this is something that I want you to understand. This is what I want you to show. I want to show that when you give me any composite number, whatever you like, it is always possible for me to find the prime number with two conditions. The first condition, n is divisible by that prime number. The second condition is that p is less than or equal to the square root of the composite number you just gave me. Yes? Is that understandable? So understanding the phrase is easy, yes? But now we want to show that this is always guaranteed. Okay, so how should I say that? You tell me that n is composite. Okay? So then I am telling you that because you are telling me n is composite, I am allowed to think along these lines. I am allowed to think that n is a product of at least two numbers. Is that understandable or not? It might be the product of a lot of numbers, but it is a product of at least two numbers, yes? Okay, for example, the example that I made here, 24. 24 is a composite number. I can write it as a product of two numbers, yes? So, for example, 4 and 6, I don't know, I can write 3 times 8. Of course, I can write it as a product of two numbers, okay? This is guaranteed, hopefully. For example, if I write 16, 16 can be written as 4 times 4, yes? So sometimes these numbers are the same. Sometimes the numbers are not the same, okay? So I use different letters A and B because sometimes they might be the same, sometimes they might not be the same. So this is why I have to choose two letters. Okay. What are the conditions of these numbers? I hope that you agree with me that none of these numbers is equal to 1. Yes, because if this number is equal to 1, I didn't write it as a product. Okay, so both of them should be greater than 1. And none of them is equal to n itself. Because if one of them is equal to n, the other one has to be 1. But we told that none of them is 1. So do you agree with me? So if I give you a composite number, you can always write it as a product of two numbers. None of them is 1. None of them is n itself. Is it guaranteed? Okay. And now, of course, A and B, one of them might be smaller than the other one. So these are names. I call the smaller one A, I call the bigger one B. So is that understandable? So the conditions for A and B is that I myself call the smaller one A and the bigger one B. But on the other hand, none of them is 1. It means that both of them are greater than 1, strictly greater than 1, not equality, and both of them are smaller than n. So this is what I claim there. So when you tell me that n is composite, I can imagine that this n can be written as the product of two numbers with those conditions. Is that claim understandable?
Yes.
Yes. Okay. Now I will take this part. You told me that a is greater than 1. Okay? Now I refer to the first statement up there. Okay? Every natural number greater than 1 has a prime factor. Yes? A is a natural number greater than 1. So this means that A has a prime factor. A has a prime factor. Yes? Is that understandable? That's exactly the same sentence. But because I want to work with that prime factor, I give it a name. Yes? So A is greater than 1. According to that theorem up there, A has a prime factor, which I call it P. Yes? Okay. What is the meaning of A has a prime factor? This means that P divides A. Do you agree? Because that is the meaning of being factor. P is a factor if A is divisible by P. Okay, so let us keep it. Now I am telling you that P divides A and N is equal to AB. From these two, are you happy that I can conclude that P divides N? Yes or no? You see, A itself is divisible by P. Do you agree that the whole product will also be divisible by P? Yes? So from P divides A, because N is E times B, I can also conclude that P divides N. So let us keep it here. Okay, on the other hand, I can conclude something else. This is one of my conclusions that I made from here. Another conclusion is that, hopefully you agree with me, that the magnitude of P is at most equal to the magnitude of A. This P cannot be bigger than A, otherwise A cannot be divisible by P. So this is one constant, let me call it number one, let me call this one number two. Yes? This is, just keep it and forget it, okay? We wrote it down here. Now we go back here. I take this one. Okay, if you are thinking that why Babak is doing this, I don't know. I am following this guy who actually proved this. So that was the creativity coming from that person who was able to construct this kind of argument to prove his argument. Yes, I am just following him. Okay. So there are two questions in mathematics. Understand the logic. This is the role of the teacher. I can only explain you the logic. But another question is that how on earth I myself can come up with that idea. I cannot answer that. If I could answer this question to myself, then I will be a Nobel laureate. So that's, I want you to understand. There are two different questions in mathematics. Yes? How I come up with this idea, I don't know. I cannot answer that question. Of course, if you practice more, the chances that you can come up with similar argument increases. But it's not guaranteed. But me, when you are looking at me, because this is, by the way, from my experience, I see that when I say I want to do this, you are always thinking why. I told you that in mathematics, there are a lot of scratch paper work that you don't see. The final result is polished and published. Yes? So that's the way that I'm doing it. So you need to learn that when I'm saying something, you just follow the logic. For example, if I go from here to here, you don't understand why, you can ask why. But if why I am writing these things, you don't have a right to ask why unless you sit down and listen to the logic to see if it works. I want to take this bad cycle from your heads off, yes? So you need to understand this is the logic. You have to wait, see why it works. But in each step, you can ask why. Okay, if I go from here to here, you don't understand, you can ask why. But why I am doing all these things, it is not clear. Yes? The reason is that I am following that guy. If there is another problem, either I succeed to find a way to do it or not. And then I fail. Yes? I just want you to understand. Okay, so A is less than or equal to B. Do you think I can write this? So here you can ask why. Yes, you can ask why this is true, that from here I can conclude this. Okay, but is that understandable? Because if A is less than B and A is positive number, I can multiply both by the same A and keep this inequality the same. Yes, if A is less than B, do you agree with me this one is also less than this one? Yes. And there is another name for A times A. People write A squared for that. And then less than or equal to A times B. And then, of course, if A squared is less than or equal to AB, from our previous knowledge, we know that A is less than or equal to square root of N. Okay? So if you don't understand how I go from here to here, from here to here, from here to here, you can understand. You can ask me why. But why I am doing these things, you have to be patient and see why it works. Okay? So is that understandable for everyone? Okay, so this, let me call it number 3. Yes? Now look, you have some statements on the board. from comparing number 2 and number 3, can you tell me what can I conclude again? Number 2 is telling you P is less than or equal to A. Number 3 telling you that A itself is less than or equal to square root of N. What can I conclude if I want to? Yes, everyone? P is less than or equal to square root of N. So this is guaranteed on the one hand. Yes? On the other hand, number 1 guarantees that P is a factor of N. So what was my goal? My goal was to show that you can always find the prime factors so that first, it divides N. Second, P is less than or equal to a square root of N. I was able to show it to you. And then now it becomes clear why I did what I did. Yes? This is, I want you to understand, this is a little bit more advanced mathematics. So, why we do it like the one we did here on the board is because someone else did it. It doesn't mean that you should always do the problems that someone else did it. This depends to you. If you want to be on top of the research, you have to do something, other people follow you. So that's what it is, yes? Okay. Any questions? And then I hope that you understand, is that understandable now? Okay, and now, do you understand this is the consequence? Because this claims that as soon as n is a composite number, there should be a prime factor which divides n and is less than or equal to a square root of n. It means that if you cannot find such a p, it means that n is not composite. It means that n is prime. Is that clear? Okay, good. Okay, so that was what I wanted to mention, but let us now go to the lesson today. This is a very, very simple lesson. Okay, so then we want to talk about first the greatest common divisor, which I show it simply as G dot C dot D, greatest common divisor, and I'm so lazy, so I just drop the dots. So GCD, greatest common divisor. So I think I will start with give you an example. It's a very, very simple lesson. So let us consider two numbers. Let me give you number A to be 12. Let me give you number B to be 18. The question is that what is the greatest common divisor of these two numbers A and B? Yes? Okay, it's very simple. I want to tell you how we can find it just looking at this, the meaning of these words. Okay, so let me write divisors of A. Okay, positive divisors. So let me so I always mean positive divisors in this context. So what are the divisors of A? A is 12. What is the smallest number in my list? If you stick to positive ones, yes? No? The smallest one is always 1. Yes? What is the divisor? When I'm asking you to list the divisors of A, I mean list the numbers so that 12 is divisible by them. Of course, if you say 2, minus 2 is also okay, but I want to keep only positive ones. Yes? So the smallest number in my list here is 1, because 12 is divisible by 1, and I cannot find a smaller than 1, any number with that property. What is the next number in my list? 2. Yes? What is the next number in my list? 3. What is the next? 4. The next? 6, and the next? 12. Is there any other numbers so that 12 is divisible by them? Yes? If you exclude negative ones. This is the only list that I have. So divisors of 18. So let us write the list. Divisors of B, 18. What is the smallest one again? 1. The next one? 2, 3, 4, 5, no, 6, 7, 8, 9. Yes, and then the next one? 18. Yes, so this is the list of my divisors for 18. This is the list of my divisors for A. So that is the word divisor. But there is another word called common. So it means that I want to see which one of them is common to both of them. So the list of common divisors. So what is the list of common divisors? 1 is a common divisor. Yeah, so I write 1 in my list of common divisors. 2 is also a common divisor. And then 3 is also a common divisor. And then 6 is also a common divisor. Yes? But I do not have any other common divisor. So this was divisor, this was common, and then greatest common divisor. It means what? Greatest common divisor. It means that in the list of common divisors, which one is the highest value? Which one is the highest one, which is 6. So the greatest common divisor is 6. Yes? Okay, so if I ask you what is the greatest common divisor, it means I found the biggest number so that 12 and 18 are simultaneously divisible by that. Not the other way around, be careful. 12 and 18 are divisible by 6 simultaneously, and I am not able to find a bigger number so that 12 and 18 are divisible by that simultaneously. Yes? Is that clear? So let us look here. And then, do you think this makes sense if I say least common divisor? Does it make sense? And if it makes sense, what is it? 1. And why we don't study it, I don't know, have you heard about this least common multiple somewhere else? So you see, we don't say least common divisor. Why? It's always 1. So there's nothing interesting about it. Because the list of divisors always start with 1. So 1 is always a common divisor, and it's always the smallest one. So if I want to talk about LCD, it's always 1. So there's nothing interesting about LCD, what we call about common, the GCD, okay? Another question is that, which is important to know, there is another terminology I want. Let me ask you, what is GCD of 3, so let me write 9 and 4. So try to imagine, the list of divisors of 9 is 1, 3, and 9. The divisors of 4 are 1, 2, and 4. The common divisors are just 1, it's just 1, and the smallest one is, the greatest one is 1. So the GCD of 9 and 4 is 1. Okay? So if the GCD of two numbers is 1, we say that A and B are relatively prime. Or relatively prime. It doesn't mean they are prime. Okay? As you see, 9 is not a prime, 4 is not a prime, but we call 9 and 4 are relatively prime. It means that if you write this as a fraction, it is not reducible. So you cannot simplify it more. Okay? So if I have GCD of two numbers equal to 1, this is a terminology. It is, I don't know why they have said prime, but they are relatively prime. It means that you cannot find any common divisor except 1 for them. And it means that if you write this as a fraction, that fraction cannot be simplified further. But if I write this fraction, 12 over 18, this can be simplified. Okay, how? By dividing the numerator and the denominator by GCD. So I divide this by 6, it becomes 2. Divide this by 6, it becomes 3. If you don't divide by 6, if you divide by 3, it gives you 4, it gives you 6. Still, you can reduce it more. But if you divide by GCD, then it is the end of the story. It cannot be reduced more. Yes? So GCD is something that we discussed about. Of course, I will tell you a little bit algorithmic way to find this, but before doing that, let us go to least common multiple. Let me take these two numbers, and now I want to find least common multiple. So again, the problem is that A is 12, B is 18. This time, I want to find least common multiple, not least common divisor. Yes? Again, let me describe the words. Multiple. So what should I write? I would write multiples of A. So what are multiples of A? What is the smallest multiple of 12? Multiple means that number should be divisible by 12. You see, in divisor, 12 is divisible by these. When I say multiple, I mean numbers that are divisible by 12. What is the smallest one? 12 itself, if you want to consider the positive ones. Okay, what is another multiple of 12? 24. What is another one? So let me write some of them. Does this list end? No, it will continue forever. Yes? So this is the list of multiples of A. And then, again, the same story, multiples of what? B. What is the smallest one in the list? 18, the next one, 36, the next one, 54, 72, I don't know, 90, 108, and etc. Okay? So, multiples. Now, the second word is the common. So, list of common multiples, yes? So, what are the common multiples? 36 is one of them. 72 is one of them. Of course, you see that if you continue this list, you will have more. Yes, for example, what is the next one coming after 96? 108, and 108 is also a common multiple. So if you want, you can add this one. And I hope that you agree that this list might also go forever. But now, you want to talk about least common multiple. So this is the list of common multiples. The smallest one is 36. So the question mark is now 36. So that is the least common multiple. Yes? Does it make sense if I ask about GCM, greatest common multiple? You see that this list continues forever. So there is no greatest one. There is no biggest one. Yes? So this is why you do not see GCM. And then for the same reason, you do not see LCD. Okay? Okay. Any questions here? There is a nice relation between LCM and GCD and the numbers. This is an exercise in the book. I write it here down and then you try to convince yourself. There is a very nice relation. If you have GCD of two numbers, if you have LCM of the same two numbers, and if you multiply them, it becomes the product of the same numbers. Yes? So this is a good relation. This is expressed in the book. Probably we come back to it later at some point when you have questions. But this is good to know. For example, let us check. If I take GCD here is 6 and multiply it by LCM 36, what is the answer? It's 216. Okay? And now if I multiply A and B, it also becomes 216. So the product of the numbers is equal to the product of GCD and LCM of the same two numbers. It's good to know about this rule. But if we want to algorithmically find this LCM, of course this is always possible, but it is a little bit boring if the numbers are big, okay? But if I want to find them, a little bit more efficient, so how can I do that? Okay, so let me think in that way. So let us give you A to be 12 and B equals to 18. And let me call the GCD of A and B to be D. My question is that what is D? Of course, I know D because we did it before. D is 6. But what do you mean by D here again? It means that you are looking for a number so that 12 and 18 are divisible by D. And D is the greatest one possible. Okay? So if I factorize 12, do you remember factorization? 2, 6, 2, 3, 3, 1. It always ends with 1. So 12 is nothing except 2 to the power of 2 times 3, and you want to have this d. Pretend that you don't know d yet. And then you have here, if I do it for 18, it becomes 9, 3, 3, 3, 1. So 18 is 2, 3 to the power of 2d. Okay? Now I ask you, which numbers as factors you can put in the denominator? Remember, you want to make this number an integer. You want simultaneously make this number an integer, but you want to write the biggest possible d. Okay, think in that way. For example, do you think in d there can be a factor of 5? Can d include a factor of 5 in itself? Because if d includes a factor of 5, 5 multiplied by something else, no matter what is that something else, these 5 survive in the denominator and cannot be an integer. So in the factorization of d, 5 cannot be there. Because if 5 is there, so you see that d is a number, you can write it as a product of prime numbers, okay? Do you expect, let me start from this one. So let me ask you, do you expect that 2 is in this factorization? Yes? Because the list of numbers that I have, prime numbers 2, 3, 5, 7, etc. You might expect that there is a factor of 2 in the factorization of d, because this 2 to the power of 2 and this 2 can be simplified without making this a non-integer. Still, it is possible to be an integer. Do you think there should be a factor of, it might be a factor of 3 here as well? Yes, so there is no violation so far. But do you think factor of 5 can be here? Factor of 7? None of the other factors can be here, because if 5 or 7 or something else is here, even if this one and that one are simplified, gives me an integer, the remaining factors will be remain in the denominator and they are not integers. Yes? So this means that 2 and 3 are the only prime factors that you can expect in D. Yes? Yes? Is that understandable? You want to imagine a D so that 12 divided by D is an integer, 18 divided by D is an integer, 12 consists of 2 factors of 2 and 1 factor of 3, 18 consists of 1 factor of 2, 2 factors of 3. So D is also a number. So this can also be written as product of prime numbers. But which prime numbers? You cannot expect to see 5, 7, 11, etc. in the factorization. Because if this appeared here, there is no way this becomes an integer. So 2 and 3 are, so for example, can I just write 2? Yes? Do you agree this is an integer? Do you agree this is an integer? But this is not GCD. It is just a common divisor. I want to make it as big as possible. Okay? For example, do you think I can put a factor of 2 here, a power of 2 here? For this one, it is okay. But for this one, it becomes problematic, because this one and that one will be simplified, but 2 will be in the denominator, which makes it an non-integer. Yes? So what I'm saying is that you have some limitations here. On the one hand, you want to make it the greatest number possible. On the other hand, you want to make it an integer, both of them. So do you see that this is the only option that I have? 2 and 3, nothing more. And what is 2, 3? Is just 6. And 6 is the number we got it from the other way around. Okay, now I can summarize it for you. I want you to understand this is not something that you memorize. So if you want to find GCD with this method, you factorize them and you find the common factors and put the smallest power for them. Yes? Yes? So you see, I factorize this, 2 to the power of 2 times 3. I factorize this, 2 times 3 to the power of 2. The factors are 2 and 3. The factors are 2 and 3. Between this one and that one, the smallest power is 1. Between this one and that one, the smallest power is again 1. So I choose power 1, power 1. So that is my GC. Yes? Okay, let us see if you understood this correctly. If I give you this number, so let me give you a number that after factorization becomes something like this. 2 to the power of 5 times 3 to the power of 4 times 5 to the power of 2. And you factorize another number and it becomes, say, 2 to the power of 3 times 3 times 7 to the power of 3. Okay, now if you factorize this number, can you tell me what is GCD of A and B? Yes? Yes, how did you found that? Because if I ask you what are the prime numbers involved in this problem, you say 2, 3, and 5. If I ask you what are the prime factors involved here, you say 2, 3, and 7. You find the common ones. The common ones are 2 and 3. And then the power of 2, here is 5, here is 3. You choose the lowest one, which is 3. And the power of 3 here is 4, here is 1, you choose the smallest one. So if I give you two numbers like this, the GCD is simply this number. You choose the common factors with the smallest exponent for each one of them. Yes? Okay, can you give me an algorithm for LCM now? Let us understand the same problem. So this time, let me write LCM of 12 and 18. This time, let me call it M. What is M? M is the smallest number that is divisible by these two simultaneously. So this means that I want to look at these fractions and I want to fine-tune M in a way that, first of all, it is the smallest possible number. Secondly, these two should be an integer. Yes? Okay. So, and then 12, we already know. 12 is 2 to the power of 2 times 3, and 18 is 2 times 3 to the power of 2. Okay. So, and then M is an integer. So let me write the prime numbers, 2, 3, 5, 7, 11, etc. Okay. Do you think this is possible for M to include factor 5? Yes? Be careful. Is it possible for having factor 5? Yes, it is possible, because if you have a factor 5, the important thing is that factor 5 is not relevant. If you have a lot of factors here, what you concern is that this should be an integer. If this is an integer and you multiply it by a bunch of numbers, it remains an integer. But there is another restriction. The restriction is that I want to keep it as small as possible. So this is why I don't put 5 there, because then I am making it bigger. So I want to find M in an optimal way. So if I want to find it in an optimal way, which prime factors do you think will be involved for M? You want to write something for M so that M is divisible by both of them and it is the smallest one. So which factors you put for M? 2 and 3. Why don't you choose to put more? Because you want to keep it as small as possible, okay? And then you need to fine-tune the powers. Which power do you think I use? Is 2 times 3 okay? If I put 2 times 3 here, 3 and 3 are cancelled, that is okay. But 2 and 2 to power 2 will be cancelled, 2 will be left in the denominator, so that's not okay. Okay, so which power of 2 I need? At least 2. Can I make it bigger? Making it bigger works, but because I want them to find the minimum, I keep 2. Okay? So what is the appropriate power of 3? Can I keep it 3 to the power of 1? 3 to the power 1 is okay for this one, but will not be okay for that one. Okay? So I need to increase the power. And on the other hand, I want to keep it the minimum value, so what do you think for the power? 2. Now, do you agree that this is the smallest possible M that is simultaneously divisible by them? But what is this one? 4 times 9 is 36. And 36 was exactly the number we got. Okay? So let me ask you the question here. If you understand what is going on, can you tell me what is LCM here? So which factors should be there? Remember, you want to write all possible factors so that if you put on top this one and these two below them, this is divisible, but this is the smallest one. So which factors do you think I need here? No, be careful, okay? So let me do it again. Let me call it m again. Put a below, 2 to the power of 5, 3 to the power of 4, 5 to the power of 2, and then let me write m here, 2 to the power of 3 times 7 to the power of 3. So now let me write it in front of your eyes. So which factors I really need to put in m? I need 2, I need 3. Do you agree? I need 5 and 7. Because if I don't put 7, so far it might be possible for this one, it will not be possible for that one. So I have to contain all the factors. Okay? But now you want to fine-tune the exponents. So which exponent is the minimum possible exponent? 5. Do you agree? So because if I say 3, 3 will be good for this one, but will be problematic for this one. Okay? So it becomes 5. Can I make it 7, 6? Yes, but this becomes bigger and bigger. I want to keep it as small as possible. So 5 is the minimum value that I can choose for the exponent. For 3, 4. For 5, 2. For 7, 3. Yes? So is that understandable? So if I want to summarize what I told you, if you factorize two numbers into the product of prime numbers, for GCD, you choose the common factors with the smallest exponent and multiply. For LCM, you choose the common and uncommon factors with the highest exponent and multiply. Yes, is that clear?
Yes.
So let us repeat. So let us everyone repeat, because it's a very simple thing. Yes? For GCD, after factorization is done, for GCD, which factors you choose? The common factors. With what type of exponent? The lowest exponent for each. Yes? And for LCM, you choose the common and uncommon factors with the highest exponent and multiply. Yes? Is that clear? So that is the way that you can find this. Sometimes I have seen books, instead of GCD, they call it LCD. For LCM, they call it LCD. I just want to tell you that don't get confused if you see in another book. And that is a little bit unfortunate, because what they mean is not least common divisor. You remember I told you that least common divisor is always 1. But some books you see, they write this, but they mean least common denominator. Okay? In that case, it is exactly LCM that we described here. Why is that? For example, if I give you 1 over 12 plus 1 over 18 and I ask you to find the answer, what you need to find is LCM. Okay? What is the LCM between 12 and 18? 36. And then you say 36 divided by 12 3 times, so I have to rescale this by 3 as well. 36 to 18 2 times, I have to rescale it with 2. Because this is serving as the common denominator, in that books they call it least common denominator, but it doesn't mean least common divisor. Okay? So let us not confuse you. So forget about this one. LCM and GCD, we have them. Okay? Of course, in Swedish language it's different, so this is why you have different letters in your book. But GCD and LCM, if you want to add fractions with different denominators, which one of them works for the common denominator? LCM. Yes? So that is why some books call it LCD. Any questions? Okay. And then I think there should be also possible numbers. So if GCD works for GCD, I don't think it works for numbers separated by comma. Let us check. So for example, 12, 18, and 24. Can you predict what will be the answer? GCD of 12, 18, 24?
6.
Again, 6. It means you want to say something that 12, 18, 24 are divisible by that simultaneously. Let me see if it works or not. It doesn't work, okay? Because if you see, you go here, GCD, let me type it again, GCD, and then either you have two numbers or you have a list of numbers. This is not the syntax that you need to use for a list of numbers. A list of numbers in GeoGebra is used curly brackets. So if I want to give more than 3 numbers, so I would say GCD, okay, I choose the first one, but then I put curly brackets and type my numbers there. This is my prediction, hopefully it works. So let us say 12, 18, and 24. Because when you say list, list should be included in a curly brackets, yes? Yes. Oh, 2? Oh, because I typed 26, that is right, yes? 12, 18, 26 is 2. But let me change it to 24. So what was your prediction here? Was 6. So remember, if you need more than 2 numbers, you have to put them in curly brackets because this should be a list, okay? Any questions? And then you can do this for LCM as well. Yeah, for 2 numbers, it is you just type them. For 2 numbers, you can also put it in curly brackets, I think. Yes, it doesn't matter. Oops, 12. I think it should work. Yes, it works. So I'm pressing enter. So the answer is the same. So if you want, I can make it, I don't know, 14. And that's 84. Yes, that's correct. Okay, so that is how you can do it in GeoGebra. Okay, any questions? Okay, this part of the lesson is also finished, but I will add something on Google Classroom, but there are many good exercises. I would say some of them are actually hard. So the next lesson, what I do, I will probably choose some of them and then we go through them together. Okay, because some of the problems are a little bit different in nature. You haven't used to this way of thinking yet. So this I will solve it for you. Okay, so you will continue working on your own, yes, because we have time yet. Thank you very much.